Welcome to the Beyond Chemical Engineering YouTube channel. In this lecture, we will learn about mass transfer in laminar flow. So all we know that mass transfer refers to the movement of species, which means molecules, ions, etc., from one location to another location due to a concentration gradient. In laminar flow, the fluid moves in parallel layers with no mixing between them, which strongly affects diffusion and mass transfer rates. And mass transfer in laminar flow is diffusion dominated, with predictable correlations using Sherwood, Reynolds, and Schmidt numbers. While it is slower than turbulent flow, it is crucial in microscale systems, films, and biomedical flows. Concept of laminar flow. So, the laminar flow occurs when viscous forces dominate over inertial forces, and it is characterized by smooth streamlines and no eddy mixing. And when it comes to Reynolds number, Re is given by rho u L divided by mu. When Re value is less than 2000 in pipes, then it says as laminar regime. In laminar flow, mass transfer is slower than turbulent flow because there is no turbulent mixing. Mechanisms of mass transfer. Mass transfer in laminar flow involves two main mechanisms. First one is molecular diffusion, which means dominant near interface. It is governed by Fick's first law, which is given by Ja is equals to minus dAb multiplied with dCa by dZ, where Ja means molar flux of component A, dAb means diffusion coefficient, dCa by dZ means nothing but concentration gradient. Transport occurs only due to random molecular motion. Second one is convection, which means bulk transport by flow. In laminar regime, velocity profile is parabolic in pipes or develops smoothly over plates, coupled with diffusion to determine overall mass transfer. Laminar boundary layer. When a fluid flows over a solid surface, example, flat plate. Velocity boundary layer, which means region where velocity rises from zero at the wall, no slip, to free stream. Concentration boundary layer, which means region where concentration changes from bulk value to interfacial value. Thickness of mass transfer layer delta n is related to hydrodynamic boundary layer thickness delta V. Key relation given by delta m is proportional to delta V by Sc to the power of 1 by 3, where Sc is equal to mu divided by rho dAb is equal to Schmidt number. Dimensionless numbers in laminar mass transfer. Sherwood number, which is denoted by Sh, which is analogous to Nusselt number. Sh is equal to Kl into L by dAb, where Kl is equal to mass transfer coefficient. Reynolds number, which is denoted by Re, which is flow regime indicator. Re is equal to rho u L by mu. Schmidt number, which is denoted by Sc, which is ratio of momentum to mass diffusivity. Sc is equal to mu by rho dAb. Correlation for mass transfer in laminar flow. Over a flat plate, gaseous solution, given by Sh is equal to 0.664 into Re to the power 1 by 2 into Sc to the power 1 by 3. In laminar pipe flow, constant wall concentration, given by Sh is equal to 1.86 into Re into Sc into d by L to the whole power 1 by 3. These correlations help in estimating mass transfer coefficient Kl. Film theory in laminar flow, which is proposed by Whitman. It assumes a stagnant laminar film near the interface. Mass transfer occurs only by molecular diffusion through the film. And the flux given by Na is equal to KL into CAB minus CAI, where CAB is equal to bulk concentration. CAI is equal to interfacial concentration. Effective film thickness is given by KL is equal to DAB by rho. Penetration and surface renewal theories. Refined models. Film theory is simplistic, which is steady state. Penetration theory, Higby, assumes fluid elements are exposed to surface for short time before renewal, which is given by KL is equal to under root to DAB by pi Tc, where Tc is equal to contact time. Surface renewal theory, Dankwards, considers random replacement of surface elements, given by KL is equal to under root DAB into S, where S is equal to surface renewal rate. Applications in laminar flow. Gas absorption in packed beds in low Reynolds number. Laminar film condensers in heat and mass transfer coupled. Microfluidics or lab-on-chip devices in diffusion dominates. Biomedical flows, example, oxygen transfer in capillaries. Thin film evaporation, drying, coating processes. Comparison with turbulent flow. Mixing in laminar is by molecular diffusion only. But in turbulent, it is by diffusion plus turbulent eddies. Mass transfer rate in laminar is low. As compared to turbulent, it is high. Boundary layer in laminar is thick. But when it is turbulent, it is thin. Equations in laminar is simple correlations. But in turbulent, it is more complex, empirical. Thanks for watching this video. If you like this video, share and subscribe. For more updates, follow the Beyond Chemical Engineering pages in all social platforms.